Hello, everyone. I want to take a minute to talk about light, and what I'm using here is the University of Colorado's PHET online simulations, and this one is on bending light. And first, I want to talk a little bit about Snell's law that says that if I take light and it goes through a change in medium, refraction occurs, and what that means is the light is bent toward the normal when it's going from a lower index of refraction to a higher index of refraction. On the top, the white is air, and the bottom, the blue, is water. And as the index of refraction increases, it is bent more and more and more toward the normal. And as it decreases, it's bent less toward the normal. And if it is the same index of refraction, it doesn't move at all. And there is something interesting here that is occurring on top of this, and we can see that in the next idea. But let's look at the wave representation here, because I think that's pretty helpful to understand too. So as you can see here, I have this region where I'm interfacing between the air and the glass. And it's like ants going on a line and then hitting some sludge. And as they hit sludge, they slow down in the glass, and that causes the bending to occur because index of refraction is related to the speed of light in a vacuum as opposed to the speed of light in the material we're talking about. And you can see as I move this, that index of refraction becomes a little bit easier to understand, and this amount of bending becomes easier to understand. So I can also go from we could go from, say, glass to air, and in this case I'm bending away from the normal because I'm going from a higher index of refraction to a lower index of refraction, and there is some angle, which is the critical angle, where I can no longer bend the light and be out in the air, and that's where total internal reflection occurs. So in this case, I could stick a protractor here, and I can see that it's around, 40 degrees. And if that angle is above 40 degrees, then I have no transmission. If it's below 40 degrees, I have transmission and refraction. The newer ideas that we talked about in class this week are about light and lenses. But before we get there, and it will be important to understand this later when we talk about lenses, we can also talk about the dispersion of a material. And that's the difference in the index of refraction depending on whether I'm talking about white light or what wavelength of light I'm talking about. And you can see here that white light, when I put it in a prism or a material that has an index of refraction, will bend, and it'll bend blue light more and red light less. And because of that, I end up with a rainbow as it comes outside of my prism, and it always deflects it away from the apex of the prism. But what we talked about this week was actually about lenses. And if I take, say, a converging lens, and I put it here, and I look at one ray of light, it's hard to see what's happening. But what I can do is I can put multiple rays of light there. And what the converging lens does is it takes all of the light coming in parallel and causes it to focus down on a single point. And with a converging lens, I have a focal point to the right of the lens in this picture, and that means it's a positive distance f. And that focal point is where all the light rays converge that are coming out parallel. And I could think about putting objects in place, and then we have an image distance as well, but I just want the focal length to be very clear to everyone. And we could also have a diverging lens, which is a lens that causes the light to move outward and away instead of together. And in this case, it doesn't look like it'll have a focal length, but it does, in fact. And the way we define the focal length here is we trace all those lines backwards. And all those lines go backwards to a point of convergence on the left side of the lens. And here I have what would be referred to as a negative focal length for a diverging lens. And we also spent a little bit of time talking about diopters and the power of a lens, and diopters add, and this negative positive focal point convention is so that if I had two lenses, one with a focal point of f and one with a focal point of negative f, and I put them together, that would tell me that I should have a focal length of 0, or that the light should never converge either way, and that would be this scenario. And in fact, that is exactly what I see. So light comes out parallel and goes in parallel. I'm going to make another video about the thin lens equation and how to use it, but I hope this helps you sort of understand what a focal point is and better understand divergence and Snell's law. Thanks, guys.